And I'm going to go through this, like, so what exactly do I mean by automated reasoning, and why on earth do we care about it, and how actually I do it, or how I actually do it. And so it is one of the earliest area of AI. And now, since we heard already quite much of AI, not just today, but I'm sure during the many, many months and years, that has AI made into establishing an own field. What's your take? When was AI coined as a term? So when was the term artificial intelligence coined? Sorry? In the 50s. More precisely, so it's a very good guess, yeah? So more precisely, now the question how do you round it up, but in the 50s, between the 50s and the 60s. And it actually was, back to the roots. It was kind of the beginning when you there was this there are more people there, but in the 56, there was an event in the US, and this was the first time when the term artificial intelligence was coined. So it was meant to mean like, let's have a seminar or summer school on artificial intelligence, which essentially meant like automating human intelligence using machine-based reasoning. And the father of AI, or one of the father of the AI, is called John McCarthy, and this writing there, which maybe you don't really see it there, but it's a screenshot of the writing that came out in '56, and this is really when the term artificial intelligence was coined. And so John McCarthy, even afterwards, did a lot of research, also contributed to Stanford Research Institute, which is now called SRI. And his mind, and in the mind of people that you saw in the picture, I mean, those who are computer scientists in the room, you will see you see names that are the fathers of various aspects of computer science. You have Marvin Minsky there, you have Claude Shannon, so entropy theory, and many other researchers on the picture. And clearly, what AI was believed to be in 56, or in the 50s, and think like that 50s is just 70 years ago. And ever since these 70 years, AI grew into a domain that actually changes our life much more profoundly than likely any other science has changed in 70 years. However, what AI was meant to, or was thought of in the 56, actually evolved into much more, into evolving many facets of AI. People talk about symbolic AI, and this is the closest that John McCarthy thought of. Then there is so-called probabilistic AI, and there is also connectionist AI. Now, and there are many other nuances of AI. I just put up the three which I thought the most relevant for this audience could be. And when you think in terms of what does it mean in terms of terminology? So symbolic AI is what logic is about. Or if you're more a mathematician, you would think, well, this is discrete math. 0, 1, true, false. This is very precise. Then you have the probabilistic AI, but it's more just the name tells you it's probabilistic. You have all about uncertainty, and you have Bayesian inferences. And this is what applied statistics in mathematics would do. What is the probability that despite today is not raining, tomorrow might rain? And this is probabilistic AI, you do predictions. And there is the connectionist AI, or the cognitive part, but essentially you think in terms of connections, in terms of networks, in terms of neurons. And this led to the field which is go to neural networks. And as I said, many things evolved, and I would now really say that connectionist and probabilistic AI went into this field, which is now, today's lingo is machine learning. And this is really, I think, where the work of today's laureate was seminar, and you already mentioned that when I tried to draw it to the screenshot, I could only find it in German, but I guess it's because it's a diploma, right? But this was in the 1991, and it's again a seminar work, and this led I really think that this led to the combination of connectionist and probabilistic AI that we heard about, long short-term memories, which evolved to what people now talk about machine learning. And if you're interested more on the English version, then you can also see the article out there. So what is then automated reasoning? Well, automated reasoning is about the symbolic AI. Where essentially we are more in the discrete world. And these two things together, they are also machine learning and automated reasoning. Ideally, they should coexist, that they should help each other. And this is another trend that people try to combine them and make it not just working with machine-based learning and machine-based reasoning, but let the learner and let the reasoner work together and let the monitoring between that helps the both. So put it bluntly, what automated reasoning in my definition is symbolic AI, is logic-based reasoning in a scalable and efficient manner. And the task of automated reasoning in this sense, it's really what back then also John McCarthy thought of, okay, given a problem, represent this problem in a formal language. And likely this formal language is going to be, well, a logic. And depending what logic or the language you use, the logic will be much more expressive. And once you have the problem translation into a formal language problem, then now this is where actually computers can help you. You have this formal language that a computer program can understand, can parse, and can manipulate objects with. And then once you have the problem translated into formal language, well then you do computer-supported automatic check whether this statement is true. Now again, thanks to many research and actually fathers of logic in even from Austria, so we know from Gödel. How many of you heard about Gödel? I hope quite many. So yeah, I also heard about him. So we know from Gödel and also we know from Turing and we know from many other seminal works that there are more problems out there that can be ever solved by computers. Okay? Which means there are problems there which are true, but they are open problems. You will be unable to prove them at least, but whatever technology comes out there. Okay? We just have the incompleteness results. So therefore, as a theoretical computer scientist, I'm not that worried about all the highs because we know where the boundaries are, so let's work against the boundaries, so let's work with the boundaries. So what we do essentially in my group at Wien, okay, we essentially try to develop automated reasoning techniques for planning, for proving mathematical theorems, in trustworthy software development, for establishing cybersecurity, or identifying cyber attacks, and also generating provably correct code, and many other areas. But again, as you already heard in the very first talk by our laureate, is that you cannot have an arbitrary universal model or universal automated reasoner. You have to be domain specific. And why? Again, if you just think about Gödel's result, you know that a universal prover, a universal reasoner will not exist. So just to credit the funding agencies, my research is funded mainly by the European Research Council, but by also the Austrian Science Fund, the WWF, and most of this collaboration is happening through industries from Amazon Web Services, Microsoft Research, and Certora, which is a smart contract verification company. So let me tell you why, I hope I kind of convinced this is fascinating, but if not, let me tell you a bit why actually we are doing. I gave you a few applications, but let me tell you concrete case scenarios where I don't have to convince you that software is everywhere, IT is everywhere. It's kind of like, I can tell you that our world is run by software. Like it or not, it is the truth. You're all using your computers, you're using your smartwatches, your phones, you're making decisions on online bankings. Microsoft is still one of the most valuable software companies. We are maybe relying on cloud services from Amazon Web Services or other cloud providers. And then we are having these smart digital systems that are controlling cyber-physical systems such as planes or cars. So despite all these things, and technology is really there to help us, but despite all these things, it's quite common we employ the software that is produced by many intellectuals, researchers, developers, and then you're quite common that you're facing this screen. So how many of you saw such a screen in the last 6 months, let's put it that you did something and you had to make a software update. So raise your hand if you had such a screen up. I just had it in the morning. So you do the update, right? And then you hope. So those of you who had raised a hand up. So assume that you did the update. How many of you believe that this is your last update of your life on your software? I bet 0, right? You don't even have to do a prediction. I mean, I think it's a safe bet to say 0. And why? There are various reasons. It might also be because just an error occurred during the software update. Or maybe a new error will come and a new software update will be required. So why is that? Why is, are we really that incapable at TU Wien? That, we are 600, we are at TU Wien in bachelor students starting first year computer science. And they're also, towards the end, they should be very good software engineers, and they're going to be employed by very good companies and producing their software. So does it mean that our software engineers are not clever enough, they're unable to produce good software? Or is it really the case that software is so difficult to understand? And I would tell you it's more the second. So we have very good engineers out there, but software is a very complex beast. And we just accept it. We just accept that software is error prone. And there are all these newspapers, like from the first big news when Tesla accelerated it and managed, so hackers hacked into Tesla's software device and managed to crash the car. Or very recently, actually one of my favorite software errors from the past year, it was a CrowdStrike software error. It happened last year and put everyone for 1 or 2 days into no operation. And if you start understanding what was happening there, essentially it's so-called it happened due to a software logic error. And there are many other news out there. And just to explain why it's so concrete, let me make an analogy here. So I'm not even using a supercomputer here, a very standard computer that even in schools would be used. It's a computer that has about 10 megabyte memory. Now in computers, computers operate on many things, but the smallest bit in the memory would be the smallest atom in the memory would be a bit. You store information in a bit, which has either value of 0 and 1, 0 or 1. Okay, so depending how you initialize this bit, you will have different operations. Now, if you have 10 megabyte memory, that would correspond to, roughly speaking, 10 to the power 20 million bits. Which means, if you have a 10 megabyte memory, you can encode more than 10 to the power 20 million operations, combinations. So now, if you want to make sure that your software is absolutely correct, you have to analyze 10 to the power 20 million bits. And I would say this is a huge number. And if you don't believe it, here's an analogy which I like to make. The number of atoms in the universe is about 10 to the power 80, and we still don't understand the combinations of what's happening in our universe. So it's quite unlikely that, it's quite likely with very small changes in a well-working software, you are introducing an error in a combination of the 10 to the power 20 million operations. So, we have to accept that errors will always be there, we just have to work for that the critical errors do not occur, and that's the idea that we try to do in automated reasoning. Let's try to minimize or reduce the numbers of errors in software production. So the task is of how you ensure that software is error-free, or put it more bluntly, how do you, so it's in the past, error was always considered that if the software is not working, it's an error. But during the many years of software development, an error now actually has has a very complex meaning. Or a software working correctly, it's not just because you don't access, for instance, you access a memory, an uninitialized memory, that's an error. But is this the only error that you should worry about? For instance, if I can, as a software engineer or as a computer scientist, your task could be that write a cyber attack. Now, if this is your task and you accomplish your cyber attack, then the cyber attack will be correct according to the requirement. But is it is it a trustworthy software? It's more an ethical question. Well, I would say a cyber attack should be not trustworthy. So the question of ensuring of software being error-free turns into the question, okay, how can we ensure that the software is trustworthy? And here's a much more complex question. It's not just about logic, it's also about sustainability, it's also about computing power, it's also about ethical questions. And some part of it we try to establish using automated reasoning, and this is the technology, logic-based reasoning, which is essentially in bigger companies, it's deployed, a billion calls of a day are happening on automated reasoning engines. So let me give you a few concrete examples. But before that, let me recall that, so don't hope for a general recipe, because as we know, this would be a great thing to have. I give you a software, and at the end, your task is show that the software is trustworthy. You plug the software into the automated reasoner, and you hope for a miracle. And then the miracle tells you that the software is trustworthy, or the software is not trustworthy. This would be the output of the automated reasoner. Now we know Actually, I told you Gödel, but it's also before Gödel, even from Turing. We know that this is an impossible dream. Now, a universal reasoner, a universal computer cannot exist. So what we need, again, going back also to Professor Kovacs, is that you need domain-specific reasoner. You need domain-specific engines for various domains. Now, how do we do it? Well, we know we cannot do, so that's how our working recipe in automated reasoning, nonsense 65. So it's just 5, 6, 6, 5, the two numbers are flipped. And what is happening in logic, I give you a problem and you want to show is it true, or put it differently, is it satisfiable? If it's satisfiable, you give me a proof. In many cases you don't, and then you just try it again. You try again, and hopefully, if the problem is provable, you hope for a proof. And we develop our own automated reasoner. It's called the vampire tool, and it's regularly we need a theory proving competition in the area. So now let me give you two examples in the landscape of planning and cybersecurity. And I will start with very simple examples, and depending how you grasp further, I will go into more and more complex examples. And let me start with it's a bit related to planning a meeting or to planning a conference. And it's one of the tasks that we also give to bachelor students. And this is, I would say, if the bachelor students are unable to solve this problem, then maybe they should not study computer science. So here's I simplify the problem very much. So we want to plan a meeting, and we have to determine the list of participants. So who are invited to this meeting, or who are allowed to be invited to this meeting. And there is this rule that if you are a close collaborator to someone, then you should be treated, so close collaborators should be treated fairly. Either you invite all the collaborators, or you invite none, because you don't want to produce conflicts in a team. And I just make it now, give you two instances. I tell you that Eva is a close collaborator of Felix, and Marie is a close collaborator of Georg. Because I just give you 4 names so far. Then personal matters come into the game. If Marie is invited, so Marie is such that if you invite her, you have to invite Eva. However, Eva does not care whether Marie is invited or not. So she's absolutely neutral. She has no preferences. Now further comes, so there's some conflict, and Georg and Eva cannot stand each other, so you cannot invite both of them. And then you want to invite Georg and Marie. This is as an organizer, this is your preference. The last line is your preference, the other is from the participant. So what is the list of the participants? So you want to invite Georg and Marie, right? That's coming from me as an organizer, I want to invite the two of them. Okay, but now Georg and Marie, they're close collaborators, so therefore they have to be invited together if they're invited, right? But now if I invite Marie, then I have to invite Eva. That's the second line. However, Georg and Eva they cannot stand each other, so they cannot be invited together. So just from 4 constraints, so if I just remove this constraint, I could still produce a list of participants. I add one more constraint, and essentially I create a list, or I create a problem that from being true or satisfiable becomes, just with one constraint, becomes immediately unsatisfiable, and the more I will add will not change the output, it will still remain unsatisfiable. Now there might be even more participants there, I don't care, it's just enough with 4 participants to find the conflict in a very simple constraint solving problem, which is encoded in so-called propositional logic. And then the list of participants, it is an empty list, which is a well-defined structure in mathematics. So no participant is invited. It will be not a successful event, but at least no one will be harmed and no one will be angry. So what these kind of problems, you can formalize these problems in the simplest logic that is still useful, and it's called propositional logic. And just because it's simple, it doesn't mean that it's useless. Propositional logic, this is, for instance, one formalization. You will start introducing so-called Boolean variables. And again, this corresponds to the bit representation. A variable will have either value true or value 1. It's true or 1, or false and 0. Okay, all I need to do, 0 or 1. I'm only working over zeros and ones. So just to show how I will not go through the formalization, but for instance, this would be a logical, just one aspect how I would tell you, well, if I invite Eva, then I will have to invite Felix and vice versa. Okay? If I don't invite Eva, I don't invite Felix either because they are close collaborators. And this is what logic tells you, it allows you to formalize in terms of operators. And the similar things you can put, if you invite Marie, you have to invite Eva, but it's not an equivalence, it's just one directional implication. You put all this together, you have these five constraints, and you can pass it to an automated reasoner in propositional logic, which is called a SAT solver, one of the powerful tools out there. It can work with millions of variables, and it will tell you it is unsat. Now, this is a simple problem, and propositional logic is simple because it's either 0 or 1, which means it's also decidable. If I give you a problem in propositional logic, you can always design an automated reasoner, so-called SAT solver, where it will tell you whether this problem is true or not. However, just because we know it in theory, in practice it's an empty complete problem, which means you don't even have polynomial time algorithms to solve propositional logic problems. So even for the simplest logic out there, it's very hard to do very efficient algorithms unless you do some heuristics and you do further optimizations. Now, let me show you another example. And this now goes a bit with mathematics. And it goes all with hash functions that you're using in security. So I exerted a lot because I also wanted to make a connection to long and short memory that we also try to mimic in an automated reasoner. And I gave you this sentence, or I gave you this property. So I take a non-empty set of natural numbers, and I claim that it has a lower bound. Now, natural numbers are the numbers 0, 1, 2, 3, 4, 5, 6, and so on. There are infinitely many natural numbers, but they always have a lower bound. Okay, so the lowest natural number is 0. But I don't tell you I'm working always with an entire set of natural numbers. I'm just saying, okay, I'm giving you a non-empty set of natural numbers, and it should have a lower bound. So who of you believe this is true? I also believe that. I kind of gave you the argument, right? But now the point is, in automated reasoning, it's not just a belief. I want to have a certificate. I want to have a proof of it. So if it's true, give me a proof, and give me a proof in mathematical logic. So let me show you how this connection will be done in our own solver. I'm going to run vampire on this. But by the fact that it's every non-empty set, now it's not anymore propositional logic, I'm quantifying over objects, and I go into first-order logic, which is known to be semi-decidable. So now I'm just running vampire on it, and I gave 20-second time limit, and it's just producing one clause after the other. It's a knowledge graph. I'm just deducing consequences. And essentially it found a proof. This is a refutation, and it found a proof in 9 seconds, and the proof kind of contained 150,000 formulas. So it's a bit too much. So instead of 20 seconds, I gave shorter memory, or shorter time. I gave only 8 seconds. And I ran the prover again, and still found the proof. But now from 150 went down to only 77,000 formulas because it didn't have so much time. And okay, let's give less time. Let's give it 3 seconds. And let's see what it does. It should still find the proof. Still found the refutation is the proof. But now it's 1.3 seconds. And I can try one more. And yeah, let's just do once more. And now it still found the proof. But now only 17,000 formulas have been generated in 1 second. Now coming back to human-level intelligence and machine-level intelligence, you still need a human there, but it's unlikely that any human will be able to generate 17,000 formulas in 1 second. At least I would be unable to do that. And this is actually where I think computers can help humans, but also humans should help computers, by fine-tuning the parameters how this automated reasoner works. If they give the automated reasoner too much time and too much exploration space, in 20 seconds, it found the proof in 8 seconds, but with a proof which which was quite huge, 150,000 formulas. Many of these formulas are useless. It just explored the search space. So I usually make this analogy that this is exactly what students do, or we are doing, also researchers, when we are preparing a paper for a deadline. You tell me that the paper is in 3 months, I will do so many other things because I have so much time. Tell me the paper is in 3 hours, I will surely work on my experiments to make it to the deadline. And that's exactly how you can fine-tune an automated reasoners. The parameters, either to be on time, on memory, on selections of formulas, selections of literals that you're going to apply, it affects very much proof search. We are not going to change the result whether if a formula is true. No matter what parameters you're using, it should be remaining true. But whether you use the right parameters, you might not find the proof because the proof is explosive. So maybe to wrap up, I wanted to give you one more example. So remember that the planning example was on propositional logic. This was on first order logic, already hard enough, but unfortunately when you do security, it's not enough to work in first order logic. You work in higher order logics because you're talking about cryptographic protocols with heavy mathematics, and in addition you have cryptographic secret keys that tell you, let me just tell what's going on here. You have this very simplistic program there. It's abstracted a lot, but essentially it computes how many bits you're storing in this HW. Okay, and the HW is like a secret key. It's a Hemingway that is heavily used in cryptography. Now a cyber attacker comes, introduces noise in your cryptographic protocol, and if it's not that bad, the Hemingway should still remain the same. How do you check it? Well, you take all possible combinations, all possible permutations of the noise, and make sure that the computed Hemingway over the array A, or over your memory A, remains the same. And let me just conclude this. It means you have to reason about permutation of the entire array, or the entire cryptographic protocol, but permutations are not expressible anymore in first order logic. You have to go to higher order logic. So you lose even semi-decidable, you are completely undecidable. Let me skip this one. So what I wanted to convey is that automated reasoning is a fascinating field. It requires mathematics, it requires logic, it requires software engineering. It can be extremely fast if you do it properly. And what is more important, it does not hallucinate. So when it tells you it's true, it gives you a model or it gives you a proof that is checkable, and it should be correct provided your reasoner is correct. I think it's a fascinating area, again, thanks to Professor Hofreiter. There is this emerging effort that people require, okay, people know how to do automated reasoning in various logical formalism, and we have experts in machine learning, so why don't we combine the two of them and try to get the best out of it? It's a fascinating area. The project in Austria is called the Bilateral AI project, which is led by Professor Hofreiter. Other people would call it Neuro-Symbolic AI, but essentially it's this cross-product of machine learning and automated reasoning, and I'm sure in the next years we have many more results from worldwide and also from Austria. And now just concluding words, is it hard? I don't know if it's hard, but it's fascinating. However, as a computer scientist and then also as a parent, I think informatics or computer science is coming too late in education. So therefore, I'm committed to bring informatics into schools, and we started this so-called Abenteuer Informatik für Volksschulen. But essentially, we teach kids planning, satisfiability solving, just did together. Kids can solve it, and they will immediately answer something. Even if it's incorrect, they will answer, and they are happy to revise their answer. And we do planning, and this is how it looks like. Essentially, we do planning. It's almost like Lego playing, but they have to kind of plan the shortest path between two trajectories and instrument a robot which is already kind of pre-trained on their data set. And they will also understand sometimes the robot makes a mistake, and then they understand, well, actually human reasoning is needed to guide machine-based reasoning. So I hope I convinced you that automated reasoning is fascinating. It's even more fascinating if you combine it with machine learning, and if you're interested in one of the workshops, then please just come at the table. Thank you very much.